Obviously, it's a linear phase FIR filter. We know that if we consider the phase response between the 2 points called as cutoff frequency. Okay, we have 2 points called as cutoff frequency. The cutoff frequency is indicated as omega c. Okay, there in the beginning generally we said omega naught, but here we refer to it as a cutoff frequency. So between the cutoff frequency points omega c and minus omega c, we have linear slope. Okay, we have a linear curve having a slope which is equal to minus alpha. So the phase is said to be linear. Okay. An ideal low pass filter with a linear phase having a slope minus alpha and cutoff frequency omega c. Okay, please remember the term omega c is cutoff frequency and the slope is said to be equal to minus alpha. This is very important. Okay, the frequency response for ideal low pass filter we remember to be hd of omega is equal to e power of minus j omega alpha. As we know, slope is minus alpha. This is true for magnitude of omega less than omega c. So if the frequency is lying in between minus omega to omega c, only then this equation is applicable. Correct? Beyond that, the slope, the slope doesn't exist. So what is the value of the phase? It is 0. The term doesn't exist, so it is equal to 0. Okay, the term is equal to 0 for frequency between omega c to pi. Okay, so between 0 to pi, it doesn't have a value. Okay, this is the ideal one. Now, the corresponding impulse response. Okay, this is frequency response. Okay, now I want impulse response. The corresponding impulse response hd of n is found as follows. Okay, so we know the relation, students. hd of n's dtft is hd of omega. Okay, if you take dtft, we get hd of omega. Now I know hd of omega, I have to get hd of n. I have to take inverse discrete time Fourier transform. Okay, so this is what we are doing here. This is inverse discrete time Fourier transform. Therefore, hd of n, impulse response of the ideal low pass filter, by definition of inverse dtft becomes 1 by 2 pi integral with the limits minus pi to plus pi. hd of omega is the input. hd of omega is the input. Then we multiply with the exponent e power of j omega n. See, in dtft formula, we have e power of minus j omega n. In idtft inverse formula, we have e power of plus j omega n. And integration is with respect to omega. Therefore, we have d omega. Okay, so just remember. So in the definition of dtft, we are inserting the value as hd of omega. That's all. Okay. Now, next part, we are aware what is hd of omega. So we have defined hd of omega to be equal to e power of minus j omega, e power of minus j omega alpha. So this value we are inserting in place of hd of omega. And we know that the limits also have to be changed. Why we have to change the limit? Because omega is restricted between minus omega c to plus omega c. Correct? So as far as the curve is concerned, only between minus omega c to plus omega we have this value. From omega c to pi, answer is 0. Therefore, the limit is restricted to between minus omega c to plus omega c. Next part is simplifying. How can you simplify? You can see that 1 by 2 pi integral e power of j omega. We combine the powers. Okay, after combining the powers, you can write it as n minus alpha. E power of j omega into n minus alpha d omega. So this is the integral, and this particular integral, if you solve this integration, the answer, the solution for this integration is hd of n. It becomes sine of omega c into n minus alpha. I repeat, sine omega c into n minus alpha divided by pi times n minus alpha. Okay, this integration, if you solve it, this integration gives you the answer, which is sine omega c n minus alpha divided by pi times n minus alpha when the value of when the value of n is not equals to alpha. Why n should not be equal to alpha? Because if both are equal, then this value becomes 0. You get sine of 0. Okay. So we do not want that to happen. So sine of 0 is equal to 0 and denominator also becomes 0. So 0 by 0 we'll get. So this is not applicable when n and alpha are same. So when n and alpha are different, only then you can apply this. What happens when n is equal to alpha? Suppose n is equal to alpha, how do you get that answer? We just see, it's very simple. So when n is equal to alpha, n and alpha are same in this integral, correct? N and alpha are same. So n minus alpha will be 0. When n and alpha are same, it is 0. So we get e power of 0. Okay, so in the integral, we get e power of 0. So what is e power of 0? It is 1. Okay, and the integration of 1 with respect to omega is omega. The integration of this is omega. Then we have to apply the limits omega c and minus omega c, and that gives you the answer 2 times omega c divided by 2 pi. Okay, the answer is 2 times omega c by 2 pi. 2 cancels and your result is omega c by pi. Okay, so this is a very important result, students. This has to be used in each and every problem of FIR filter using windowing technique, whether it is rectangular, Hamming or Hanning. This part of the solution will be common. We start with ideal filter. We always start with ideal low pass filter. Then we work and get other types of things. Okay, so this is very, very important. Okay, so this result here and the procedure told here is common. It's a universal procedure for most of the problems. Okay, so we start with this. Please remember, we start with hd of omega equals e power of minus j omega alpha for omega less than cutoff frequency, 0 between cutoff frequency and pi. Okay, then we take the impulse response by using the definition of inverse discrete time Fourier transform. Therefore, the formula says 1 by 2 pi times integration between minus pi to plus pi hd of omega e power of j omega n d omega. Now substituting for our particular case, we know the expression is given by e power of minus j omega alpha. The integration is with the limits minus omega c to plus omega c. Just combining the exponents, we can get e power of j omega n minus alpha. And if you solve this integral, probably you know when you integrate that particular expression, integral of an exponent is it's also a exponent, correct? So we get an exponent, right? And if you simplify it, the answer of that simplification will be a form which is sine of omega c n minus alpha, okay, divided by pi times n minus alpha if you attempt to solve this integration. Okay, and this is applicable when the value of n is not equals to alpha, and when the value of n is alpha, then you get the answer which is omega c by pi. So that means that hd of n plot will look like this. The plot of hd of n will look like this. Okay, so this is something like our sinc function. Okay, this is something like our sinc function. So the shape you can see, it's like sinc. Okay, correct? No? So its shape is something like a sinc. So at n is equal to alpha, it peaks. The peak will be at omega c by pi, and on either side the value is decreasing. Okay, the value is decreasing on either side, and it peaks at n is equal to alpha. This is what is observation from these two equations. Okay, so this hd of n we discussed to be infinite. This hd of n is said to be infinite. It keeps on going on in both sides. Okay, this is infinite. A causal FIR filter with impulse response h of n can be created by taking the infinite hd of n, multiply it with the finite window. W of n is finite because it is restricted between 0 to n minus 1. Everywhere else the value is 0. So what happens when you multiply the infinite impulse response with the finite window function? Your result becomes both finite as well as causal. The result becomes both finite as well as causal. So the procedure is like this. We take hd of n into w of n, and the answer we get is h of n. Now why are we writing it as w of n here? because we know based on the choice, you may choose rectangular, you may choose Hamming, you may go with Hanning, you may go with Bartlett, you may go with Blackman. So I don't know which type you have chosen. That is why generally we are depicting it as W of n. When you know the appropriate type, we have the expression, you can calculate what W of n is, then you can multiply it. Okay. So we have HD of n given by sine of omega c times omega c is cutoff frequency, n minus alpha slope, right? Divide by pi times n minus alpha into W of n. Okay. So this, when you multiply it, it becomes h of n. See, previous equation was that for HD of n. The HD of n was given by this. Okay. For n is equal to alpha and for n not equal to alpha. This is what is given. Now next step is multiplying. So when you multiply both by W of n, the end result is called as h of n. So this is what is h of n. The objective of any design is to get h of n. Okay. Designing means you have to calculate what is h of n. So as you can see, there are two cases now, when n not equal to alpha and when n is equal to alpha. When n is equal to alpha, it is given by omega c by pi times omega n. So the linear phase filter, the value of alpha must be chosen such a way that the h of n is symmetric or it is anti-symmetric. We have derived this condition. So when it is symmetric only, then you will get linear phase, or when it's anti-symmetric only, will get linear phase. So either of these two conditions must be satisfied. How? By carefully choosing the value of alpha. Okay. Now, since HD of n is symmetric about n is equal to alpha, and W of n is symmetric about n is equal to n minus 1 by 2. Okay, so this is the important point, students. HD of n is symmetric about n is equal to alpha. Okay, impulse response, HD of n is symmetric about n is equal to alpha. The window function is symmetric about the midpoint, that is n minus 1 by 2. Therefore, to maintain the relation, we have to equate both. Okay, therefore a linear phase for h of n means alpha should be equal to n minus 1 by 2. Okay, so n is the length, the size, or the order. Okay, it's the order of the filter, or it's the length of impulse response. So alpha is related to n like this. Alpha is equal to n minus 1 by 2. So if you're given the value of n, we can calculate alpha. Okay, this relation is very, very important. We have to satisfy this particular condition. Now, here's a table summarizing all the facts that we have learned. The table shows name of the window function, transition width. Now, what do you mean by transition width? Already we spoke in the 4 different scenario. The width between the passband and stop band. How much is it? How much is the width? The stop band edge frequency is called as omega s. The passband edge frequency is called as omega p. What is the difference between passband and stop band? That region is called as transition width. Okay. Now transition width, how it is for the different cases, we can see here. For rectangular window, the transition width is not very high. It is 4 pi by n. But for the remaining cases, Bartlett, Hamming, all three, it is 8 pi by n. It is double. The transition width is more for Bartlett, Hanning and Hamming compared to rectangular. For Blackman window, it is still more. It is 12 pi by n. Okay, 3 times. This is double. This is 3 times the width. So having more transition width is not desirable. We don't like actually. Okay, but we can't help it. But transition width is like this for the various window cases. The stop band attenuation. Okay, how much is the stop band attenuation? We have seen the difference between passband and stop band, right? So passband we say is 0 dB. Stop band we say is what is measured, right? So the difference for rectangular window was 21. For Bartlett was 25, for Hanning it is 44, for Hamming it is 53, and for Blackman is the highest, which is 74. So in this count, the winner is Blackman. Blackman is the best window as far as the attenuation is concerned. Stop band attenuation is very high, so it's a good window. But what is the penalty you have to pay if you have to go with the Blackman window? The width, transition width here is more. So the more you have transition width, the order will also become more. Okay, so we have to be careful here. Okay, we have to be a little careful. So more transition width, higher the order. Okay, so rectangular in that case is the best one because transition width is very less, but it is a poor performer because attenuation in the stop band is not very high. We want more attenuation. So the choice is very simple. So if you are asked a problem, a question like this is asked in the exam, the question states that you have to choose a window. They don't say. Mostly in the exam they give you the window type and say you design. Suppose they don't mention the window type, but they say that the minimum stop band attenuation should be equal to, let's say, let me say 22 dB. Okay, somebody says in the problem statement, give me minimum value of attenuation in the stop band equals 22 dB. Now, which one would you choose? The problem states minimum value should be 22 dB. Means it can be more than that also. See 40 dB, 50 dB, all these numbers, 80 dB, they are more than 22. But minimum is set as 22. That means that if I say 22, anything in this list from Bartlett onwards will satisfy. Rectangle is 21, I cannot go with 21, at least I should have 22. So according to the list now, I could actually go with Bartlett, Hanning, Hamming, etc. Okay, I could go with anyone. Correct? So now as a designer, I can choose any one value, Bartlett, Hanning, Hamming, okay, Blackman, anything I can go for. But how would you choose? You have to be wise, okay, you have to be smart. So 25 is greater than 22. So this also satisfies, Bartlett satisfies the criteria. So if I go with Bartlett, the transition width is better compared to that of Blackman. Blackman had 12 pi by n, okay, delta omega, that is difference between the passband edge frequency and stopband edge frequency is equal to 8 pi by n. For Blackman it is 12 pi by n, that is more. So this is comparatively okay. So we'll pick the value in the list which is highest up in the list, which satisfies the specification. So this item which is highest up in the list, that is Bartlett, satisfies my 22 dB requirement. That's why I'll go with Bartlett. I hope you got the idea. Similarly, if 30 dB is asked, give me a minimum value of attenuation, stop band attenuation 30 dB, then the choices will become Hanning, 25 is ruled out, it will not work, okay? Hanning, Hamming, Blackman. Which one will I go for? I will go with Hanning because it's highest up the list and it satisfies my value of 30 dB. Okay, if you are given 60 dB, then the obvious choice here is only Blackman. The rest will not be capable to serve the purpose. Okay, so this is how we have to design. Okay, so the procedures steps for designing is this: select the window type from the table I just showed you, to be the one highest up the list and such that the stop band attenuation exceeds AS. AS will be given in the problem, attenuation of the stop band. Okay, so the one which is in the list and which satisfies that requirement we will select. In step number 2, delta omega is called as transition width. It's a difference between omega s and omega p. This is the transition width. This is determined, okay, and from this we can find the order, right? How we can find order? Okay, so we have seen the table here and the table clearly said that delta omega equals omega s minus omega p is equal to 4 pi by n for rectangular. If you know delta of omega, can you not find the order? You definitely can, because you know here clearly that delta omega is equal to this. Okay, right here, delta omega equals to this. You know delta of omega. Pi is a constant. Can you not find n? You can. So this way you can calculate the order. So once your window type is chosen, once you are aware of transition width, you can calculate the order. So this is what we do next. We determine the order. We will find the order. Okay. So second step. Okay. Step number 2 is to find the order. Okay. First step, given the value of AS, given the minimum value of AS, we check the table, we select that window type which is highest up in the table. Okay. In step number 2, we calculate transition width, which is delta omega. It's a difference between omega s and omega p. And from that we obtain the value of order. So n is chosen to be greater than or equal to k times of 2 pi by delta omega. See, why k? Because for different window functions we have different values. So generally we have written as k. K is equal to 2 for rectangular, Bartlett Hamming has K 4 and Blackman has K value 6. So don't worry, you can remember the value. You can remember 4 pi by n, 8 pi by n and 12 pi by n very easily. So from that you can calculate n. Okay, so order is also found. Step number 3, we start with this, we specify the ideal or desired frequency response. Now, what do you mean by desired? We know for a low pass filter how it is. So HD of n is desired. If you know that if you take the DTFT, okay, so DTFT of HD of n is HD of omega. Therefore, if you want to find HD of n from HD of omega, we have to go for inverse discrete time Fourier transform. Already we have seen that integration and the formula. This is for ideal. Next part, in step 4, we obtain the impulse response HD of n of the desired IR filter by evaluating the inverse DTFT of HD of omega. Okay. For an ideal low pass filter having the following frequency response, okay, this is how we had studied. This is ideal low pass filter. The inverse discrete time Fourier transform gives you HD of n. This is also we have studied. This we have learned. Okay. And step number 5. Okay. Because of what is called as smearing effect, I'll explain what it is. Because of the smearing effect of the window on the filter response, the cutoff frequency of the resulting filter will be different from omega p. Say ideally I want omega p, passband edge is cutoff frequency. But due to an effect called as smearing effect, the effect may be slightly different. I'll show you what is smearing effect. Okay. See, this is the response of an ideal low pass filter, HD of omega. This is the response of the window. We already seen. It's like an impulse, sinc function. Okay. When you convolve the two, it causes a spreading in terms of frequency. It spreads. Okay. This was very compact. Now this is spreading. Okay. This spreading in terms of frequency is called a smearing effect. Okay. Now what happens when this spreading happens? Normally omega c is chosen to be the midpoint between omega p and omega s. Okay, we carefully choose the midpoint. Okay, now why we choose midpoint? It is to compensate for that spreading. Okay, so omega c is said to be equal to omega p plus delta omega by 2. Why delta omega? Delta omega is the width and we want midpoint. So midpoint is given by omega p plus delta omega by 2. Omega p added with half this width. That is your omega c. Okay, and we know that the condition to be satisfied for a symmetric HD of n is alpha value should be equal to the slope alpha should be equal to n minus 1 by 2. So these two equations we have to we should know and we should apply it. Okay, and finally the impulse response of the FIR filter is found by truncating HD of n using the window function. So do it for the ideal first. And finally, the ideal HD of n, we multiply with the finite window called as W of n, depending on the window function, and that answer is called as H of n. So I hope we have learned the steps how to obtain the impulse response of a FIR filter and how to design an FIR filter. These are the design steps. Problems shall be solved and we shall learn how to apply these techniques. Okay, the techniques have been discussed, but application we have to discuss.
Thank you all.